Hello viewers, this is the Top Lab. In this series, you will see a man playing with football, another man cutting a wire, a football on a shelf. Alright, anyway, welcome viewers to today's Top Lab. Before the experiment, have you ever used your water pipe to water your garden? Well, it's quite relevant to this experiment. In today's experiment, we will use the voltammetry to measure the resistivity of a certain material. And that material is called the copper wire. So, let's invite my colleague David to introduce the theory part.
Okay, we all know that the resistance is directionally proportional with the length of the wire conductor, which has the shape of a cylinder, and inversely proportional with the cross area of the wire. So, we got an equation that R resistance equals to P, the resistivity, times the length over cross area. Okay, now how to realize this equation? Okay, let's just think about a pipe. Consider there is a pipe, and this piece of shit is water. Let's just think it's water. So once the length of the pipe is longer, it actually takes more time for the water to pass that pipe. So same thing in the resistivity. So the length of the conductor, the wire increase, the resistive force increase, so the resistance increase. Think about another example. We got a same pipe, but it actually smaller pipe with shorter diameter, and we got same amount of piece of shit, piece of water to pass this smaller pipe with same length. Okay, so this time the cross area is actually smaller, but we can see it actually takes more time for this water to pass that pipe since the cross area is smaller, and in the same second there is a less volume of water to pass the pipe, so the cross area is inversely proportional with the resistance. We got the equation. Now we need to conduct the equation about the P, the resistivity, which is the object today. So P actually equals to A cross area times the resistance over the length. By using this equation, we got that. However, we need to further specialize this equation since we cannot directionally measuring the cross area of the little copper wire. We need to further specialize this equation into in the terms of d, the diameter, and the resistance and the length. So we got the equation: a quarter of pi times d squared times the resistance over the length of the conductor. So that's basically the equation we're gonna use today. Now let me introduce the Steven, who's in charge of the circuit part.
Right, David is right, but the circuit part is also important because we need to measure many data. And in today's experiment, we will have many components. And one of them is called the main power supply, which is a big box right there. And we will connect through wires to connect a variable resistor. And yeah, let's just draw this component. And after that, we will connect to an ammeter to measure the current in this circuit. Yeah. After that, we will connect the most and the main character into this experiment, and it's called the copper wire. Let's just draw this sign. And back to the main supply. And the most important thing is we need to also measure the voltage. And so we will use the voltage sensor, which cross the copper wire and back to this end. So that's the basic main whole circuit in today's experiment. So we will measure the current and voltage. Now we will to figure out the resistance of this copper wire. It's the voltage over the current. Now it's very easy, and let's invite my colleague Justin to introduce the component, and let's do the experiment.
Okay, for this experiment, we have multifunctional power supply connected with the slide rheostat. It adjusts the resistance value by sliding the slider and used to control the magnitude of current or voltage. And those are called electric transducers. This is current transducer connected in series with the slide rheostat. And this is a voltage transducer connected in parallel with the wire. And this is a sensor delivering those data to the computer. And this is digital caliber. I will use it later to measure the diameter of the wire. So now I'm going to record 10 sets of the data, which are the voltage and current passing through the copper wire. And after that, we will calculate the mean of them to minimize the errors. So now let's do it. First, I'm going to use the meter tool to measure the length of the copper wire. Okay, it's about 10.9 centimeters. And I'm gonna use the digital caliber to measure the diameter of the copper wire. It's just about 0.26 millimeters.
After measuring, we got that the length equals to 0.106 meter, while the diameter equals to 0.00026 meter. Now we have gotten every single type of data we need for deducing the resistivity. The potential difference, the current, the length of copper wire, and the diameter of the copper wire. They are all listed here, and yes. Now here we got the resistivity of the copper wire. You can see they are mostly the same. 0.00033, and we also got some 20 and 30, 48. Okay, so these arrows are within control since this circuit doesn't completely follow the ohmic rule. Some little clips maybe got more resistive due to the heating or less. But most roughly the resistivity of the copper are the same and is exactly this value.
That's all.
Great for us.
See you next time, my son!